Now we will start with the Unit 5 thyristor. Thyristor comes from the Greek word called door. You know what is a door, right? Door can open or close. Similarly, the thyristor is just like a switch. We can open it or close it. So they are called solid state semiconductor devices with four layers of alternating N and P material. All of you are familiar with semiconductor materials in your electronic circuit. It can be either N or P type. All of you are very much used to the two-layer semiconductor device called diode or a PN junction and a three-layer semiconductor device called as the transistor, NPN or a PNP transistor. Here we will discuss four-layer semiconductor device within the family of PNPN devices or four-layer semiconductor devices. The SCR is of greatest interest today. SCR is silicon controlled rectifier. The common application of silicon controlled rectifier or SCRs are relay controls, time delay circuits, regulated power supplies, static switches, battery chargers, etc. Now, moving to the operation of a basic silicon controlled rectifier. This is the graphic symbol of an SCR with its corresponding connections to the four-layer semiconductor structure. See, it is having three terminals, anode, cathode and gate. So, an SCR has three terminals, anode, cathode and gate. Look here, this P, it is a alternating PNPN four-layer structure. This P corresponds to anode, this N corresponds to cathode and the gate is this P. So these are the different types of SCR available. The operation of SCR you will understand best by splitting the four-layer PNPN structure into two three-layer structures or through two transistor model of this SCR. See, look here, this PNPN, the four-layer structure, I just cut from the middle. That I am getting it as PNP and just cutting from the middle and NPN. So it consisting of two transistor, a PNP transistor and NPN transistor joining we will be getting the SCR. So one P, that is the anode, this N corresponds to cathode and this P corresponds to the gate. So the two transistor equivalent model of this SCR is shown in the figure. So this is an NPN transistor. The corresponding NPN transistor I will be drawing here NPN. And this is a PNP transistor. So it is PN and P. Now look here, the NPN transistor N, that is the emitter, is connected as the cathode and that is over shown here. So this will be the cathode, it is connected to ground, it is the cathode. Now the P of this NPN transistor is connected to the collector of PNP transistor. See, the P and the P both are combined and that is connected as the gate. It is shown here as the gate. So this will be the terminal of gate. So the emitter of this PNP transistor is connected as the anode. So I'll mark it over here. So this is the emitter of the PNP transistor. It will be the anode. So look here. Now the base, that means the P part of NPN transistor and the collector part of PNP transistor both are combined and together it is called as the gate. Now N, N of PNP transistor and the collector of NPN transistor both are connected together, and this P is the anode, this N is the cathode. So this is the two transistor equivalent model of this SCR. Now we will see how does it operate when we are applying a pulse at the gate. Now this is the pulse voltage we are applying to the gate of this transistor, gate of this. So here check, this is marked as Q1, this is marked as Q2. Now during the time interval from 0 to T1, the gate voltage is equal to 0. So if you are applying this voltage over here, transistor, it is an NPN transistor that is connected to the base of the transistor. So it is equal to 0 means transistor Q2 will be off. So I can say that during the time 0 to T1, your VG, that is the gate voltage you are applying, so your VG is equal to, or V gate is equal to 0. That implies that your base to emitter voltage of transistor 2, VBE2 is equal to 0. That means your transistor Q2 is off. If transistor Q2 is off, there is very limited current at IC2. That means only reverse saturation current. So that current only coming as IB1 here cannot turn on this transistor. So the both transistor are in off condition. It is called a high impedance state. That means between anode and cathode both transistor are off. So it is a open circuit like this between anode and cathode. Now what happens during T1 to T2 duration? So take the duration T1 to T2. So now your gate voltage, this is the gate voltage. So V gate is marked as now VG. So if I am applying this voltage over here, this pulse I am applying here, then my VBE2 become VG. So if this gate voltage what I am applying is sufficiently large to turn on this transistor Q2, so the transistor Q2 now becomes on condition. So when transistor Q2 is on, the collector current of the transistor increases. So IC2 will increase. When IC2 increasing, see this IC2 is only coming as IB1 for the transistor 1. So that means IC2 means that is equal to IB1. So it implies that your IB1 also increases. So it makes IB1 sufficiently high to turn on this transistor Q1. So Q1 become now on. So when Q1 is on, the collector current of this transistor increases. So this collector current of this transistor coming as the base current of this transistor. So Q1 is on implies that the collector current IC1 will increase. So this is marked as IC1. So IC1 will increase means it implies that your IB2, the base current of second transistor also increases. So IB2 increases means Q2 is already on, it will become more conducting. So what happens? The resulting action IC2, the collector current will again increase more. So resulting in IB1 increasing more. Then what happens to this transistor? This transistor will be conducting more. So it is a regenerative action. As the time goes, it becomes more and more conducting. It establishes a short circuit between anode and cathode. So as time goes, there establishes a short circuit. There is like, because it is more and more conducting means there is a direct path connected from anode to cathode like that. So it is a regenerative action. It exists a short circuit between anode and cathode. So this regenerative action results the SCR having a typical turn on time as around 0.1 to 1 microsecond, and it is a high power device. The current will be in the range, in the short time the current will be in the range of 100 to 400 ampere around, just around in 10 to 25 microsecond turn on time. So that is why SCR is a high power device. So for switching on an SCR, there should be exist a forward bias, the anode cathode terminal. Between anode cathode terminal should be in the forward bias condition, and there should be a sufficient gate pulse or a gate current for turning on that SCR. See that once SCR is switched on, it remains in on. That's the action I told, that is a regenerative. We don't want anymore the gate pulse. So even if the gate switch or gate pulse is removed, still your SCR is on as this action is regenerative. Now our next concern is how to turn off the SCR. And SCR cannot turn off by simply removing the gate pulse as I told. So how we will be able to switch off or turn off an SCR? There are two general methods for switching off an SCR. One is anode current interruption and the second one is forced commutation. So see, this is an SCR. I just mark here as anode and this is the cathode. So the anode current interruption we can, or the current to anode to cathode, if you want to reduce it, if it is going below holding current value, the SCR will turn off. Holding current means it is the minimum current required for an SCR to be in the on state. So if the current is going below holding current, SCR will be off. So how to reduce the current below holding current? If you are reducing the value of VCC, it is possible. So that means, see, the anode is connected to VCC, then it will work fine. It will be in the on condition. But if you are putting a switch and I open the switch, so the anode is detached from the VCC, so there is no forward bias exist between anode and cathode. So the current in the SCR will go below the holding current, it will turn off. This is one way. Now another one, if I am connecting a switch parallel to this SCR, so this is the anode of the SCR and say this is the cathode of the SCR. I am connecting a switch parallel to this SCR. So what happened, when the switch is closed, the current will flow in this way. If the switch is closed to condition, switch is in the closed to condition, the current will flow like directly like this. So this is, current will not flow through the SCR. So the current in the SCR goes below the holding current value, it will turn off. So that is another way to turn off SCR. Now forced commutation is the other way to switch off SCR. So here, rather than simply connecting a switch parallel to SCR, we are providing a negative voltage also to that. So as the switch is closed, the negative voltage will coming parallel across this SCR. So between the anode to cathode, we are applying a negative voltage, sudden negative voltage comes. So the current in the SCR will go down, it will go below the holding current, the SCR will turn off. So this is called forced commutation. We are forcefully turning off the SCR.